introduce matrix larger than 0. What do you mean matrix larger than 0? This is scalar. It's easy to know. If n becomes a matrix larger than 0, what does that mean? All right. If I write in terms of first order equation motion, then x1 dot equal to x2, mx2 dot equal to minus kx1 plus f. Right? Right? I want to make that to be a matrix equation of motion become this. That's my matrix equations. All right? And this one here, 0, 1, minus m1, k0, this is the matrix 2 by 2. 0, 1, minus m inverse k0. What is the eigenvalue of this? M inverse k? Are you sure? Huh? Supposed to be square root of m minus k. That's your frequencies. Right? You see? So eigenvalue of this 2 by 2 matrix, in matter of fact, is your frequencies. Now it makes sense. Now, if I ask you, say, what is the eigenvalue of a spring vibrational motion? It's the frequencies. You gotta be careful. This is important. Now you are learning how you calculate eigenvalue of a matrix, and what does that mean, the eigenvalue of a matrix? The eigenvalue of this vibrational motion will be the frequencies of this vibrational motion is the spring. So this is 2 by 2, right? 2 by 2. Now, if k equal to 0, this becomes rigid body motion, their eigenvalue becomes 0. Right? Now, think about it. What does that mean, 0 eigenvalue? What does that mean, 0 frequencies? Rigid body motion means 0 eigenvalue means 0 frequencies. What does that mean? Rigid body don't vibrate. Right. Hey. True, right? So 0 eigenvalue means they don't vibrate. But rigid body motion don't vibrate. True, true. Okay. The same thing, measurement equations. Y equal to x1. If you have measurement, displacement measurement, then your measurement equation y equal to x1. If you have velocity measurement, then y equal to x1 dot equal to x2. If you have acceleration measurement, I say acceleration measurement, then y equal to x1 double dot equal to x2 equal to this. Hey, that's important because this one, y has 2 terms. One is x1 term. One is f2. Right? So the measurement equation, if I use acceleration measurement, then you have 2 terms. One with the displacement term, one with the force term. The one with force term, m inverse 1, will be the one we call this displacement term, we call the transmission term. So you have one term come from force. One term comes from displacement. But this add together, they have the same unit. Think about that. A inverse k times x1, this is the middle, this is the frequencies. Does that mean this unit is the semiconductor unit? Yes. Now, if you don't control, these two equations you have to know. One is matrix equation of motion, that's a state equation. One is the measurement equations. Okay. That's the spring. They will never stop. Because lots of frequencies they have to vibrate. They will vibrate forever. In math. So if you look at this matrix equation here, you know that if you have initial displacement, it's going to vibrate for good. Launch it in the space and you are vibrating the space for good. Agree? If you keep watching, it won't stop anyway. At least on this side, it won't stop. And if you plot in terms of the if you go to run a math app on side, then if you plot your curve just like this, it's going, keep going. That's if this is this point is x1 somewhere out there, then it's going to be like this. So this motion represent this and that curve represented by these matrix equation of motions. All right, now, but I don't want a system that will vibrate for good. That's not good for me. If you think about your earthquake that vibrate for good, then you are in big trouble. Yeah, when earthquake come in, you want an earthquake gone quicker. In math. Now let us look at math. How does that mean in math? All right. How does that mean in math? Let's go to vibration motion with damping. Now, this is the system. This is the DMB. We call DMB. You have a spring. I have a damping called despot. Then I have a mass. I have a force as a displacement. And then I have a Newton law and Hooke's law. I have this cause damping. Three things together. That's